My name is Joe Munchak. I'm a principal atmospheric data scientist at tomorrow.io and lead instrument scientist for our microwave sounder program.
Hi, I'm Randy Chase. I'm an atmospheric data scientist at tomorrow.io, and I've been working on a lot of the microwave sounder stuff as well as AI weather forecasting at Tomorrow.
Right. So we're having a discussion about weather satellites, and in particular, the type of satellites that tomorrow.io operates, which are called microwave sounders. So just to familiarize the audience, Randy, can you explain briefly like what a microwave sounder is and how it differs from the conventional weather satellite imagery that people might be used to seeing on the internet and on TV?
Yeah, I feel like many people are probably familiar with infrared imagery or even visible imagery, like if we were up in space in the International Space Station taking pictures right out the window, and people have seen a lot of those. Or if you've seen on the local news these videos of hurricanes that are sitting there spinning out of the ocean, they're usually in the visible spectrum that we can see. Now, the main difference with what Tomorrow is offering with the microwave sounders is that we're basically taking pictures, but not in the spectrum that you and I can see in, but more in the spectrum of microwave wavelengths. And the reason why we look at microwave wavelengths is because in the atmosphere, raindrops and ice crystals either scatter or absorb or even release some microwaves. So the conventional use case there for hurricanes is in these tropical warm storms, there's actually a lot of water that emits at certain wavelengths, and we can see those at microwave images from space as well. And then contrarily, if you're looking at like a higher wavelength of, a higher frequency of microwave, like one of the channels that we offer from tomorrow.io is like 183 gigahertz, that is more sensitive to how the ice scatters away the emission of the Earth underneath it. So the warm Earth emits at some of these microwave wavelengths, and how much that energy gets scattered out kind of tells us how much ice is in that storm cloud or hurricane or whatever else. And Joe, maybe you want to touch on more on the sounder side of things?
Right. Like obviously the visible and infrared imagery is great because we have these geostationary satellites that provide images now with the modern generation. They've really upped the capabilities. We have 16 channels. You can get the data every 5 or 10 minutes, depending on where you are. They can even do rapid scans every minute. And so, how could we possibly augment that data? Right. I mean, it's hard to beat minute data with 1 kilometer or better resolution. But the answer is that the visible and infrared don't tell the whole picture, particularly when it comes to tropical cyclones, because they tend to have very dense cirrus cloud tops, and so you can see where the cloud tops are, and usually that covers a lot of the internal structure of the storm, which is where the rain bands are, where if an eye wall might be forming. And the microwave data has always been really critical for being able to see through the cloud tops, even though it carries some of its own limitations. Mainly our main challenge is getting good enough resolution because the wavelengths are longer, and what that means when you're building an instrument is you need to build a much bigger aperture, whether that's a reflector dish or just the feed horn that the receivers are hooked up to. And in space generally, the cost of an instrument scales pretty linearly with its size and weight. And so if you want to build a really big antenna, that's going to be really expensive. And so that's been the real challenge in getting a lot of microwave data. In fact, up to this point, they're all on low Earth orbit platforms. And even from low Earth orbit, you aren't getting the same resolution as you are from the visible and infrared imagery. So
And Joe,
it's definitely
how much closer is low Earth orbit compared to geostationary?
Yeah, so I mean, I think it's we're talking about hundreds of kilometers, maybe 300 to 500, versus geostationary is up in the 30,000s, I think, or 40,000s.
So there's a big difference in where we're taking pictures from, based on those two things.
Yeah, so you low Earth orbit, you're constantly moving, and you circle the globe every 90 minutes. So it's great for global coverage, but you're not observing the whole disk at once. So you need to put a lot of these satellites up to give the coverage. And that's, I think, where tomorrow.io is really making an impact, because up till now, there had been a handful of microwave satellites operated by government agencies, and each agency would typically pick 1 or 2 orbits that would be their time of day, if it's a polar orbit, or maybe if it's like the NASA GPM mission, they would be at an inclined orbit, so they could cover different times of day. But because of the cost of launching these big instruments had been so high historically, there were only a handful of them, and you only got these observations, if you were lucky, every few hours, and sometimes it could be just one or two a day over developing storms. So Tomorrow.io recognized that the technology of miniaturizing a lot of the elements of spacecraft um, had been lowered over the past decade, and a lot of technology demonstration missions by NASA had demonstrated that you could do microwave sensors on CubeSats. And the cost of launches just went down dramatically because now we have ride shares, we have reusable first stage rockets, and I mean it's just a completely different paradigm than 10 or 15 years ago when a lot of these big missions that are currently in use are being formulated. So
I mean, the
you
big
know, we thought, why
difference
not?
is too, right? It's like these big government missions are school bus sized satellites, right? Compared
Yep.
to what the Tomorrow.io sounder is what, like roughly the size of a shoebox or bigger, right?
Yeah, I think it's basically the size of maybe three or four laptops if you stack them on top of each
Yes,
other.
and
So
it's
it's
pretty amazing that we're attempting to get such as good image quality from such a small sensor compared to those big school bus sized satellites.
Yeah, so let's talk about some of the images. So if you're looking at
Well,
our
Joe,
blog
before
post
we do that, do we want to talk about some recent news with the MSP and
over, I guess back in late June, an announcement went out that really made some waves in the meteorological community. Randy, do you want to talk a little bit about that?
yeah, so there historically, like Joe was saying before, there have been government sensors on orbit that have provided this microwave imagery and that have been particularly useful for hurricanes, as well as getting information about how warm the atmosphere is, or how much humidity there is in the atmosphere. And one of these missions was actually funded by the DoD, the Department of Defense, and it was called the Defense Meteorological Satellite Program. And specifically, the one sensor that we're talking about is the Special Sensor Microwave Imager slash Sounder. And so this instrument, I mean, it was put up, what, 15 years ago, right? So
Yeah, these were all launched in the early
yeah,
2000s.
so this was a quite a bit of time ago, and they were originally planned to only be in orbit for about 5 years. But historically, a lot of space missions in the past used to have planned mission lifetimes much shorter than the actual capability of the satellites. But even when it was planned for 5 and we're at 15, we're really kind of pushing the boundaries of the ability of these spacecraft. So if you think about it too, it's not so much different than your own car. A 15-year-old car is much less reliable than a 5-year-old car. And it's the same kind of principles that the instruments that are running day in and day out on top of these platforms in space, they degrade with time, whether it's exposure to space forces, solar wind, and eventually sometimes these satellites just run out of fuel to keep them actually at low Earth orbit instead of falling to Earth as part of the gravity. So there's been some news that the Air Force, I believe it's the Air Force, right, Joe? Air Force and Navy that run these satellites, they were saying, well, performance of these instruments are starting to degrade, and I'm sure there's like some security concerns because it's an old computer on top of these satellites. So ultimately, earlier this year, they announced that, hey, we're probably going to shut these off this summer. Even more recently, after some advocation from the broader weather enterprise, like meteorologists in Florida, as well across the U.S., said, hey, we really need these instruments for this upcoming hurricane season. It seems that they've extended this deadline to potentially next fall instead of this fall.
Yeah.
So
Yeah, and that's great news because SSMIS is a really amazing sensor. There are three of them that are still running. Like Randy said, they're showing their age for sure. Some of them are missing channels. The noise performance isn't what it used to be, but they still provide really great data. And not just for tropical cyclones, but also for precipitation mapping. So back when I worked for NASA, I was on the Global Precipitation Measurement Program, and SSMIS was one of the key inputs that were used. But we knew that these weren't going to last forever, and we recognized as a company that there weren't a lot of replacements that were slated, and so we knew there was going to be demand for these, and we started picking up on these small sat technologies. So the question that really comes to play is, can the small sats potentially replace, at least in some ways, or even improve upon in some ways, what we were getting from this other class of much larger microwave sensors? And that's what we wanted to discuss in our blog post.
Yeah, and
Um,
not just talk about it in words too. We want to actually show actual images from side by side comparisons of them.
Yeah, so the first image that we posted just shows a comparison, not of our satellites, but actually the tropics satellite, which is what the Tomorrow Microwave Sounder was based off of. So it's very similar to what we were getting, but we actually had this data before we had our own, and we made this image and we're comparing it to some of the others. So you see, this is a typhoon in the fall of 2023, and you can see an image from tropics, an image from ATMS, which is NOAA's flagship microwave sounder. Right now, they've got 3 of them flying, and I think there's another one that will launch next year. This is really designed for NWP applications, and so NWP and data assimilation is fundamentally sensitive to noise. So they engineered these things to have very low per channel noise and very stable calibration. And it shows in the data. If you look at the data, it's very smooth. Noise is incredibly low. It serves that application well. But one of the, if there was a compromise that had to be made, it was that they didn't have the greatest spatial resolution, because again, if you're looking at a smaller area of the Earth, then you're usually looking at it for a shorter period of time with the way that these instruments scan, and that increases your noise. So
Yeah, and
um,
the original purpose is for large boxes of the atmosphere for NWP, like you were saying. So like the original design was not to take images like where you and I are looking at and diagnosing a hurricane. It's more for these broad temperature and humidity patterns as opposed to specific hurricanes.
yeah. Yeah. Meanwhile, you have the NASA GPM mission, which has an instrument called GMI, the GPM microwave imager, and that was designed for precipitation in mind. And I think that a lot of people intuitively understand that if you're looking at, like a summertime thunderstorm cell, or a lot of these really small scale features, they happen on scales of just a few miles or kilometers, and so you need that really high spatial resolution. And so GMI has a big 1.2 meter diameter reflector, which is really big for microwave
It's almost
instruments.
as tall as me.
Yeah, and it's flying pretty low. It's flying just above the altitude of the International Space Station, so it can get a close up picture, and it shows this is, I think, about a 5 kilometer footprint, whereas tropics is around 14 kilometers, and ATMS, depending on where you are in the scan, can be 16 to 32. So
And
you really see the difference that resolution makes.
Joe,
And
you want to describe
that's,
what people are actually seeing in this image, like physically? I mean, clearly,
yep,
everyone can see the eye, but why can we see the eye, and especially in
yeah.
microwave?
These are images based off of what I call the water vapor channels, and so these are channels that are all around 183 gigahertz, which is, if you convert that to wavelength, it's about 2 millimeters. So it's pretty small, but uh, it's basically at a frequency that water vapor molecules resonate at. And so when there's water vapor in the atmosphere, it produces a signal that gets sent to these instruments. And so what we do is we take a few different frequencies close to that line to get water vapor high in the atmosphere, and then you can see water vapor low in the atmosphere if you go a little further away, and the resonance isn't quite as strong. So in a clear atmosphere, you would expect to see, okay, well, if you're really close to 183 gigahertz, you're seeing the upper atmosphere water vapor, and because the upper atmosphere is cold, those essentially the radiation you get at that frequency tends to represent a cold temperature. Whereas if you go further away, you get radiation from lower in the atmosphere, which is coming from a warmer source, and so you get a warmer temperature. And you can combine these in a false color composite such that a typical clear atmosphere looks like a dark blue in these images. But what happens when you get that scattering off the ice particles that Randy was talking about earlier is that you now have almost the opposite effect happening, where all those channels are cold, but the ones that are closer to the line are actually getting a little more influence of that water vapor above the storm. And so you get an opposite effect, and then it looks red in this image. But if for the really strong convection, it's almost the tops of those clouds are almost entirely above the water vapor, and so all the channels look the same, and it comes out as white. So there's a lot of rich detail about the storm you can see from these composites, but mainly what you're seeing is the structure of the storm and where the thunderstorms are. And again, if you were looking at maybe an infrared image, you would just see a whole lot of white, except maybe right over the eye where it would be clear even in the infrared.
Yeah, and Joe, like one of the key things remind me about hurricanes is like in order to understand its intensity, since there are an engine, a Carnot engine. I don't know if people have taken physics. It's been a long time since I've even taken physics, but we're trying to get at how much heat is being released in that eye wall from the convection and the thunderstorms, right? So like the idea would be if there's stronger convection, then it could lead to a stronger hurricane, right?
Right. That's fundamentally how hurricanes work. They're taking heat from the ocean in the warm water and then condensing it in the atmosphere and transferring that heat to the atmosphere. So another thing we can see, and we don't have a great image in this blog post, is you can actually see the warm core of the
In the
storm
hot
and
air.
how it's in the surrounding environment, because we also have channels that measure temperature as well as water vapor.
Cool.
But I think what we wanted to do was dig into more of these comparisons
Mm-hmm.
with these existing sensors to show how TMS stacks up, even though it's a CubeSat. How does it compare to these bigger sensors? So let's move on to the second pair of images, and this digs into, I think, a direct comparison now of the recent Hurricane Iona, which was a storm that rapidly intensified south of Hawaii this past week, and well, it was because it was a small storm. It was poses a real challenge for all these microwave instruments, because the eye might just be 1 pixel wide in a lot of them, which you can see here. So I'm looking at the second image now, and the top row is showing just a single channel again of one of those water vapor channels. So it's a channel that all these instruments have, both TMS, SSMIS, and ATMS. And so you can really see an apples to apples comparison of the data quality and resolution between the channels. And the storm looks quite similar among all three. You're seeing the same features. You're seeing the rain bands in the same place. You're seeing the eye. The differences are that SSMIS, it's you can see it's maybe a little noisier because again it's an older instrument. That doesn't prevent you from seeing the storm features at all. It's really just for those very fine water vapor details. And if you were trying to get an exact water vapor profile, it's at the instrument resolution, it's probably not the best instrument for that anymore. Meanwhile, you can see ATMS looks very smooth. There's none of these speckle or noise or even striping noise, which TMS has a little bit more of. But overall, they look pretty similar, and you're getting similar resolutions from them. And you can see that in the composite image below as well, which is the same scheme that we showed before. Anything you want to add to that, Randy?
No, I just think it's remarkable I mean, it is a much newer model if you think about it that way, but it's pretty awesome that you can get such a similar structure and detail from vastly different sizes of satellites. And we got remarkably lucky too, or maybe it's not lucky because we'll talk about the constellation in a minute, but the fact that we had a scan almost at the same exact time as one of these DoD sensors.
Yeah, so let's talk a little more about the constellation next. And I think this is where TMS is really exciting, because if you're comparing to other sensors, we don't quite have the spectral resolution, which like the number of channels as ATMS, which has 22 channels, and TMS only has 12. We don't have the spatial resolution of SSMIS at some of our lower frequency channels. So they're about 15 kilometers at 90 gigahertz, and ours is about 30 kilometers. But where we, I think, have an unprecedented capability is in the temporal resolution. And Randy, can you explain why this is so important for applications like monitoring tropical cyclones or precipitation?
Yeah, we were talked about earlier how like the geostationary satellites are always kind of there, and they take pictures every 10 to 15 minutes depending on where you are in the globe. But like we said before, sometimes you can't see that lower core of this tropical cyclone that could be critical in telling you how fast the wind speeds are underneath it. So if you were relying on just the traditional microwave sensors that have been on orbit, which are like a handful we mentioned before, you could go, on average, I think it was at 3 to 6 hours at least between scans. and sometimes even longer. I think the example we had from our colleague at University of Wisconsin-Madison was that there was actually a 10-hour gap between the pictures of Iona, and the TMS sensor kind of hit right in between them, which was nice. And
Yep.
I think the underexplored space and why hurricane intensity forecasts have really struggled. So I'm not sure if people are familiar with hurricane forecasting, but we've done a really good job at improving where hurricanes will go. And this is attributed to the satellite era in general. Our traditional weather models can get the large scale flow of the atmosphere pretty correct. So if you think about these hurricanes moving through the large scale flow, it's a lot like a spinning top in a stream. The stream kind of guides the main direction of that spinning top, but ultimately knowing how fast that spinning top is spinning is not super controlled by the large scale flow. So the underexplored or researched part of hurricanes that I think we might be one of the key ways of getting access to the information of, is this hurricane going to intensify rapidly in the next 24 hours, is knowing how it's been changing recently. And these 3 to 10-hour gaps of images is just not enough imagery to see the patterns of hurricanes before they start to intensify or decay. Would you agree, Joe? That I think that's kind of
Yeah. Yeah. A lot of times, if you, have this typical 4 or 6 or even 10-hour gap, if you're looking at the structure from one pass to the other, the rain bands are in a completely different place.
mm-hmm.
It's not something that you can just sort of interpolate in between, like you might be able to with if you had a better refresh rate. So yeah, it's really critical that we're getting these, that we're going to get this higher resolution. And yeah, I just like this animation showing our global coverage now, because it's,
And this is with
it's
less than
not a,
half of our planned fleet, right?
yeah. So this was when we had enough satellites up, like, let's see if we can make just a 6 hourly movie and see what it looks like. And yeah,
We
there's
apologize
holes
for
in it.
those who might have some issues with flashing, but
Yeah.
focus in on maybe like near the southern hemisphere where you can see some of these. They're called the storm track, right? When you see these little water vapor plumes spinning and moving along
Yep.
from west to east.
Yeah. So you're seeing atmospheric rivers. You're seeing, the westerlies in the mid latitude and the easterlies near the equator and the intertropical convergence zone. Again, all that high water vapor is showing up there as lighter colors, and then the descending air is the darker colors. And yeah, just seeing the motion and seeing this with real data. This is not a model. This is just all TMS observations. In fact, if you combine this with ATMS and SSMIS and GMI, you probably fill a lot of those gaps already. And that's, what we intend. We don't intend this to be a standalone constellation. It's really meant to augment and fill gaps and give us 1 hour refresh instead of 4 hour refresh,
Mm-hmm.
when you use all the data sources combined. And that's what we're building towards.
So, Joe, you were a part of planning TMS. I mean, so when you were choosing the frequencies, like you mentioned before, and the spatial resolution, what kind of sensor were you aiming to build when you decided on those things?
Yeah. So a lot of the limitations there and trades that we had to make were constrained around this 1U CubeSat. And that's what a lot of the engineering that went into tropics and other technologies that were developed in the 2010s, were kind of geared around this 1U, this 10 centimeter limitation, because that was a standard form factor for a lot of the buses. So you could use commercial off the shelf buses instead of having to build something custom, which is just a huge cost savings.
You make it sound like we just
And
go to Walmart and buy a spacecraft. Is that possible?
yeah, that's almost what it's like. Yeah, and you can, and just in the ride share, launch slots are very
As easy
affordable
as a
with
bus
that
ticket,
class
right?
as well. Yeah. So yeah, so the thinking was, well, we could have, maybe 2 or 3 satellites with a higher resolution, or we could have a dozen or more of the small resolution. And that's why we said, okay, we're gonna, the biggest bang for the buck we can make is this temporal revisit gap. And then, let's see where that goes, and maybe we'll be able to improve upon the spectral and spatial resolution in the next generation. And we're already making some pretty exciting plans for that next generation of instruments.
Do you think that so far, since with the progress you've seen, do you think you've been successful in the planning and what you've been able to do with it?
Yeah, the program's been an amazing success, and honestly, my biggest surprise has been just how well calibrated these instruments are, and how they approach the stability of these much larger systems. Because it's one thing to build an instrument that can make measurements and you can get the imagery out of it, but to show that it's accurate to within less than a degree, in many cases just a few tenths of a degree of something like ATMS on a long-term basis, I think is really a great testament to the engineering team, both at Tomorrow.io and MIT Lincoln Laboratory that did a lot of the design work for Tropics, and then took the lessons learned from that mission and applied them to TMS.
So have we been sharing this data, Joe?
Yeah, so since February, actually, we've been sharing data from two of our satellites with NOAA, and they're evaluating it for a whole host of applications. And we've had some great interactions, particularly with one of their cooperative institutes at the University of Wisconsin that does a lot of work with this type of data to estimate hurricane intensity. And they've just been really, I think, proactive and eager to work with us and set up their pipelines to work their data, and they're showing it to us. And actually, it's available to the public on a 24-hour delay. And I don't know if we want to list that address. Maybe we'll write it in the
Yeah, we
blog
should
post where
definitely be in the
people can
blog.
actually see some TMS data. Again, that's per the pilot program, it has a 24-hour delay. But obviously they're getting it in real time, and the NHE forecasters are getting it in real time too.
So I guess just to wrap up, I mean, I'm feeling pretty confident that the Tomorrow IO stuff is helped filling a gap for this hurricane season, and hopefully others agree and can look at the data themselves and give it their own evaluation, right?
Yeah, and I think in this era where you're hearing a lot about satellite programs potentially being discontinued and losing data, I mean the reality is that we're actually entering an era where there's a whole host of satellites, not just ours, but the Europeans are building towards a constellation of microwave sounders, and there's some other companies in this space as well. So I don't know. I think that you know the next few years there's going to be an explosion of data that's really more than we've ever had before in this particular type of measurement.